Bismillah ar-Rahman ar-Rahim. So today again we will start with the biofortification of staple crops. We have already talked about various crops and various elements to be fortified in wheat and rice, mainly, which are the main cereals being used as staple. Today we'll talk about millet, pearl millet, which is also a kind of a staple crop, and the pulses, which is used overall in the world. They both have also some kind of potential, and we have also some success stories which we will discuss later on. Starting with millet, you must know that the millet is very similar to phenotypically to maize, but it has a different kind of these panicles, and the grains are also very small and different. Uh, Grain per millet, it has a very high nutritional value. If we just compare with wheat, it has many good things. You can see here, so we have a bit more crude fiber here, fats are more, and we have relatively high zinc, and then we have a vitamin A, which is beneficial, and then we have folic acid. So it has a very nice nutritional value, which can be utilized if the people they are not using and they are deficient in these kind of uh, minerals. Uh, the biofortification, we know that if the varieties or genotypes, they have some variations, genetic variation, like here, the pearl millet had a very high genetic variability, and we have the varieties or genotypes which has iron content from 30 to 75 ppm, and then we have a zinc from 24 to 64 ppm. So it means that there are chances that we can fortify the millet by conventional breeding. So it was done, and now we have varieties of pearl millet in India, which has a very high iron content, that is around about 124 ppm. And we have also a very high zinc content, that is 84 milligram per kg. So this is basically what they achieved. Now, in few states of India, it has been cultivated up to 2 lakh hectares, and they are getting up to 70, 90 ppm iron, and the similar 60 to 70 ppm zinc, so they are achieving. Uh, then there were also experiment or studies that whether the increased amount of iron and zinc, that has some nutritional benefit to the population. So the study was conducted in India, and they found that, and they fed the school going students for around about, I think, 6 months, and after that they analyzed, uh, and they found that there is a very good absorption of zinc and iron to the population. If we compare with control, we can find here the high value of grain. For example, grain zinc content 84, in control that was 43. Then the dietary zinc, mean whatever they are eating, the amount of the pearl millet which was given to the students, so they were taking 5.8 milligram per day, and in control, so they were getting 3.3. And then they have a absorbed zinc 1 as compared to control 0.7. Then the grain iron was 124 as compared to 46. Then the dietary iron again, and then the absorption of iron, and then the absorbed iron, so that is again high than the control. And the grain phytate content, which is very important for iron and zinc, especially to enhance the bioavailability of these two. So that was less. The less amount of phytate increased or enhanced the bioavailability of zinc and iron. Please turn off your mic. But instead of that, it is not easy, or we have some constraints for the utilization of pearl millet in India and in Africa. Perhaps the people, they are using the pearl millet, but there are certain constraints. For example, we have a gray color. The gray color is basically, it's not light in most of the people. It has very less aesthetic value if we compare with the other the breads. The shelf life is very poor because it has more fats, and there is oxidation, and then it converted to dark color. So and then of course that smells very bad, and the shelf life of flour mean the pearl millet flour, so that has also a negative effect to be utilized by the masses. Then the rapid development of rancidity, it is also a kind of oxidation, then bitterness in the flour, then quality of meal deteriorated rapidly if the grains is decorticated and degrinded. Means if that is ground, there is a more oxidation of that, and then the quality of meal that is deteriorated. Basically, the nutritional values that is also decreased. The lipids of the meals release free fatty acids and peroxidase on getting hydrolyzed and oxidized. So these are basically a few things which are restricting the utility of pearl millet. But the people, they working on the pearl millet, so they have identified a few processing technologies that can help to enhance the shelf life and to reduce the oxidation issues and the the bitterness of the pearl millet. For example, the dry milling. If you dry mill, if your pearl millet is very dry and you are milling dry, you are not adding any moisture along with. So in that case, you debran. The bran in case of the pearl millet, so that is not a good thing because it has a high phytate content and it has also some fats. So if you debran, means you remove the bran of the pearl millet, it will not only enhance the quality but will also enhance the bioavailability of the minerals. Then the malting decreases the sugars and increase the mineral bioavailability. We have already discussed malting and bioavailability. Then the blanching shelf life enhanced by reduced enzyme activity. In blanching, generally they keep the seeds in boiling water at 98 degrees centigrade for 30 seconds only, and then dry it at 50 degrees centigrade. So it will also reduce the enzymes because there are fats, and the enzymes, they are working on the fats, so they are basically deteriorating the quality. Then popping, reduce the enzyme activity and enhance the shelf life. Popping, you know that you are eating the popcorns. You can do just popping, just putting it on the heated salt, and then it will pop up and the enzyme activity will be reduced, and then you can just grind it and use it as a meal. Dry heating treatment, that also decrease the lipase activity, which is involved in lipid decomposition. So there are these ways which enhance the quality. And then the last one, that there is very less demand of pearl millet in bakery items, but there are studies and they have used in various bakery items like biscuits and the other things and the breads, and they get very good response because if you use it in that, so that will reduce the enzyme quality, enzyme activity, and the bitterness of that has also been reduced. And because in the bakery item we also add other things, so that will also enhance the or reduce the bitterness. So these are the basic way by which we can promote the pearl millet, and the people they are working on that, because the only biofortification is not uh, a target, because we have to feed the people. If we are preparing some items which are very good and have a high nutrition value, but the people they don't like it, we have to consider that. So this is also a allied part of biofortification. So that was all about pearl millet. Now we have pulses. We all know what are the pulses, and in our daily life we have a part of pulses in our nutrition. In some areas the people they use more pulses, in some areas the people they use less pulses. The pulses are also used in many dishes in various parts of the world. The nutritional value of pulses, so that is also very surprising, and you can see that the high concentration of iron, even magnesium, phosphorus, potassium, zinc, copper, and folate. You can see here astonishingly that the mote bean, then the lentil, the mung bean, even the chickpea, so they have a very high concentration of folate or folic acid. So we also have zinc and iron, that is also very high. So these are the things which basically which we need to include in our uh, daily diet. So it has very significant role in human nutrition, and in various part of the world. So its inclusion is varied. For example, in India they are using more pulses as compared to Pakistan or other part. In Africa, sub-Sahara Africa, so they are using more pulses. In Latin America they are using more pulses. If we just compare the nutritional value of pulses or legumes with the cereals, you can observe here that this is for macronutrient, and these are the legumes, and these are the cereals. So we have a significantly high concentration of macronutrient, potassium, phosphorus, calcium, magnesium. So they are significantly higher as compared to cereals. And then if we consider the micronutrients, again, we have a very high content. For example, in chickpea, we have a high concentration of the micronutrients like zinc, iron, copper, manganese. In soybeans, we have a high concentration. In lupins, we have high concentration of these micronutrients. This is very, very important to consider legumes for further enhancement of nutrition value. If we consider the folate content, you can again see by comparing with the cereals that we have a very high folate content in the legumes as compared to cereals. In rice, we have a little bit, but we don't have much in other cereals. If we just consider the proteins, the essential amino acids, so again you can see here that in the legumes they are very high in these essential amino acids. So in this way we can compare and we can see the significance of legumes in our nutrition and to be part of our nutrition. So the people they are already using pulses in different parts of the world. You can see here in the Oceania, the Australia and the near parts, so their average consumption is 12 grams, and in South Asia we have 33. In Africa they have 19. In Sub-Sahara they have 33. So in Sub-Sahara Africa, Latin America, and in South Asia, we have also, almost a similar consumption. But if we consider the South Asia, for example, uh, so the Indian, they are using high rate of pulses in their daily life as compared to Pakistani. In Bangladesh, they are using a high amount of pulses as compared to Pakistan. So it means in South Asia, so we have a less consumption of pulses, but India has more. So that's why in South Asia, we in the previous slide we have seen that we have more consumption, mean the average consumption. So now we come to the global production. This is only for chickpea, and we can see here that the only India, they are producing 8.8 million tons. So they are the highest producer of chickpea in the world. Then we have Australia, and then we have also Pakistan. Uh, but if we see here the kilogram per hectare, so that is very less for Pakistan, even with, comparing with India is also very less. But the reason is that we are not taking care of much because we are sowing in the desert area without any irrigation, so without any fertilizer addition. So that's why we are getting very less average, because we are not taking care of more. We are not considering its value, and even we can do a lot more if we consider it really a necessary part of our life. So again, in pulses we have also variations. The people, they have identified the various concentration of these. For example, iron, this is in common bean. In lentil, they have also variations. Then in common bean, chickpea, in pea, the mutter, so they have also very good range of iron. Zinc, again, we have also the variation in almost all the pulses. Selenium, we have a variation for that. In carotenoids, we have also a strong variation. For example, 311 to 880 ppm, the range for carotenoids. And then for folate, we have also again some variations. So all this tell us that there is a scope of biofortification, especially the breeding, to enhance the nutritional value of uh, these pulses. Although we have already high concentration, but again we can increase further, and we can have some improvement in that, because if we have a high concentration, we will need less amount of that to fulfill our nutrition values. So there are also some studies on the agronomic biofortification, foliar application of selenium in peas. It enhanced the concentration in the grain. You can see here the sodium selenate dose. That was I think that was the foliar application, and it enhanced the selenium concentration in the grain. And not only in the grain, but also in the cooked peas, so there was also a high concentration. There is an increase, although it's relatively less than that of raw, but again it has a sufficient amount of selenium. It means the cooking of the peas, so they have very less effect on the reduction of selenium content. Then we have also, this is our own study, and this is submitted and almost accepted, and we have done with the seed coating, and we have observed seed coating, osmopriming, hydropriming, and we found that the seed coating can give us a very good content of zinc in the chickpea. So we had two different varieties, desi chickpea and Kabli chickpea. And then we also found the bioavailability, and the bioavailability was also higher in seed coating as compared to other treatment. The bioavailability is calculated by finding out the phytate concentration in the grams, and it means whatever is getting into the seed, so that can be bioavailable to the humans. Then there was another study on chickpea. So they use soil application of zinc, and they had also enhanced concentration. Or not only the soil application, they also use the foliar application, and they use different sources. For example, zinc EDTA, and zinc EDTA basically is very soluble and can easily be taken up by the plants. And there is a less immobilization of that, so that's why their intake is more, and the grain in the grain the concentration is higher. So we can compare here with the straw concentration, that the application to soil or foliar application not only enhance in the straw but also in the grain. So it means there are a great chance of biofortification, agronomic biofortification, if you just add to the soil or foliarly apply to the chickpea plant. So that can be gathered into the grains. So still the work is not sufficient. The people are working on that, and it's this work is in infancy. And I think the 2 years back there was a very good article from Canada, that the Canada can lead the if they can biofortify the legumes or pulses, so they can supply it to the whole world. So the people, they are very enthusiastic, so they are working on that. There are various strategies by which we can enhance the concentration of minerals in the grain. For example, we have a germplasm, we have various genotype, we can do that, we can select that, we can select the desired phenotypes, then we have a genomics, QTLs, genetic diversity, GWAS, we can do a lot to find out the markers for that. Then we have also transgenic approach to find out the genes and to express it. So the people, they have already worked on that, and that there are options to do that. And some people, so they are also working on that. So then we have also some of the regulatory processes, the bioavailability, efficacy, then the varietal approval and release. So because if someone develop a varieties, there are issues of regulations. So then we must have defined target for that in which area we want to enhance the nutritional value. For example, iron, zinc, or selenium, or other folate, whatever we need, or vitamin A, we can also do that. So all these are basically the strategies by which we can speed up the biofortification of legumes, and we can improve the nutrition of the population of the world. So lastly, there are very good prospects of pulses biofortification. In recent years, the biofortification has been used to enhance the iron content of beans and lentil. You can search out a song which was composed in Africa. I think in the earlier lecture I talked about that. So they have iron fortified beans, and then the people, so they were being fed on that, and they improved the iron concentration or iron content in the humans living there. So they were very deficient to that. And then so just to promote the people that to use that biofortified bean, so they compose a song. You can hear on the YouTube, just write beans iron content song. There are a few keywords and you can find it that. If you want to hear, you can. Global research priorities in pulses include biofortification of pulses. There are various organizations which identify the priorities for the research. So pulses has been included in that for the biofortification. Common bean has been approved a good source of iron nutrition in Africa, as I told earlier. So that is a very, very, very good success story. So that was all about today. In the next lecture, we will talk about the biofortification of cassava, which is also a staple crop of Africa, and maybe the biofortification of potatoes and sweet potatoes with vitamin A. So that also has been tested in Africa, and they have improved the nutritional value of their food. So thank you very much for today's lecture.